Let's get started with our last long talk of the day by Holger on statistical analysis of performance scaling.
Thank you. Pleasure to be here. So I want to start this by just acknowledging that I've had the great opportunity and the joy to work together with some very talented people on most of the work that I'm going to talk about. Here they are. You might recognize one or the other. And I'll try to call out their contributions as we go through. So what's the best algorithm for matrix multiplication? Anybody knows? Currently. Not sure that I'm up to speed, so I thought I'd check with you.
Best in what respect?
So, any serious takers? No? All right, I think it's this one here, François Legal, 2014. And it's O of n to the 2.3728639. All these decimals are pretty important because that was an improvement over what was best the year before by Virginia Wasilewska-Williams, n to the 2.372873. So there's a difference in the fifth decimal in that exponent there. And all these methods and some others are actually based on a breakthrough method by Coppersmith and Winograd from 1990, which achieves O of n to the 2376. And that was actually the first major breakthrough after the algorithm by Volker Strassen from 1969. And as I was digging this up, I found something very interesting, namely that Strassen originally was a statistician. And he actually discovered this algorithm here in Berkeley while he was visiting in 1968, just around the time when my parents sort of discovered me. So I feel very related to this. And it's interesting because essentially these three algorithms are the state of the art, but nobody uses them. And the reason for that is that the constants that are hidden in the big O notation are so big that some people who looked at this in detail determined, and I actually was corresponding with Virginia Williams about this as well, that these algorithms on modern computers in the foreseeable future will never actually be practical because the constants are too big. So what do people really do when they multiply matrices? And I think we all do. They use either Strassen or, in fact, if numerical stability is an issue, they use the naive O of n cubed. And that's where we are. So this is not to diss theoreticians at all, but it's to point out that within this big O notation, sometimes important things get hidden or neglected. And we sometimes tend to forget about that, and it's good to be aware of this. Now, of course, the other thing that I should point out is that the big O notation sometimes does give us pretty nice results. For instance, for 3SAT, there is a very nice result from 2011 by Timon Hadley, Robin Moser, and Dominic Scheder that shows that 3SAT in the worst case can be solved in O of 1.32065 to the n, which is a lot better than 2 to the n actually. If you graph this or calculate it, you'll see that this actually makes a huge difference. Doesn't explain quite why modern SAT solvers are so amazingly effective, but it makes you realize that sometimes you can be a lot better, of course, than you naively think. And this actually does mean a little bit more, although nobody uses that algorithm either. Okay, so we're all interested in algorithmics. That's sort of the interest that we share. And algorithmics has two branches: analysis, where we assess, characterize, and ultimately hope to predict performance, and design, where we build algorithms with desirable properties, and ultimately we're interested in optimizing performance in some meaningful way, right? And that's the quest on which all these people whose results I just mentioned have been. I do empirical algorithmics, which is exactly the same thing, has exactly the same motivation, but it uses principal techniques from statistics and heavily relies on tools for machine learning and optimization to talk about algorithms that are otherwise weakly accessible or inaccessible to conventional analysis, and also to talk about the constants that often are actually important. So the rest of this talk will be about empirical algorithmics. There's two things that I want to share with you today. The first one is about analysis, and the second one is about design. So let's talk about analysis first. You all know the TSP. I don't have to introduce that formally, bunch of cities. We assume that they're in the plane just to keep things simple. And actually we'll assume for the rest of this talk that they're in a unit square in the plane and that they've been randomly sprinkled there, although we relax this assumption a little bit later. And we want to find a shortest round trip that visits every city exactly once. So there's a famous and very good book on the TSP by David Applegate et al. From 2006. And in this book, they provide a lot of interesting theory, a lot of very interesting pragmatic approaches. And in the end, they come up with an algorithm that actually still is up to this day the state of the art in exact TSP solving. So if you want provably optimal tours, that's what you use. It's called Concorde. And then they evaluate this empirically because they want to know how well it actually performs. And so what they do is they generate these RUE, random uniform Euclidean instances, 10,000 of them, up to a size of about 1,000, and then they drop the number of samples to 1,000 because it becomes pretty expensive. And here they show us the mean of the number of CPU seconds it takes to solve these instances. And you can see that it starts pretty harmless with 100 cities, and then it goes pretty big at 2,500, as of course we would expect, right? And so then they show a nice graph like this. And they say about the graph, the plot of the mean values in this figure indicates that the running times are increasing as an exponential function of n. Can you all see that? It's a semi-log plot, right? And they're essentially saying this curve here levels off, asymptotically approaches a straight line, and therefore it's exponential scaling, which is what you would kind of expect from a TSP algorithm, right? So what I want to argue is that this is pretty much what most people do to empirically characterize the scaling of performance, to do the empirical equivalent of a big O analysis for running time. But I will argue that you can do a lot better. And I think doing a lot better has a lot of benefits and relatively modest costs. And so the first thing we should realize is that really, when we talk about scaling, we talk about models, right? And the model that these folks here have in mind is this one here, A times B to the n, a two-parameter exponential model. Because that's exactly what corresponds to the straight lines in the semi-log plot. Now, in statistics and in general in science, it's always good to not just have one model, but to compare models, right? Because ultimately, you want to see whether one model is better than another. It's very difficult to evaluate models in the absolute. We'll come to a point pretty soon where we can do this in this particular setting, but it's very nice to be comparing models because that makes life typically easier. And so just for the heck of it, we'll throw in a polynomial model here, also two parameters, so that it has the same degree of freedom, A times n to the b. So it's actually a monomial model, but we all know what we mean here, right? And so here is another plot of this, a little cleaner because I recreated it from the data in the table. And so now we can try to formally understand how they come to a conclusion that this exponential model fits well by actually fitting an exponential model using a normal numerical fitting procedure, numerical optimization procedure to determine the two parameter values for our two-parameter exponential model. And the red curve is what you get. And that's probably exactly what these guys drew by hand and said, clearly it's exponential, right? And you can see that too. Now, what's interesting is, first of all, you might wonder, why does it fit so well here and not so well there? That's because we're doing least squares fitting. And here the numbers, the differences are very small. Here the differences, you can't see very much, right? They would have to be very big indeed to see them. So it really kind of intuitively focuses on this representation on fitting these points well, which is a useful thing. So what happens if we fit the polynomial model, just for the heck of it? Look how interesting that is, the green curve, right? The green curve intuitively fits the data points as well as the red line, but qualitatively shows an interesting behavior here that actually kind of qualitatively mirrors what the real curve is doing, while the red curve is not doing that. So in already one sense, that green model is better. But of course, that's not how we evaluate models. How do we really evaluate models? What would you do if you had to quantitatively do this?
Give the next point.
Sorry?
Do the experiment for the next point.
Very good. So you use the model to extrapolate, right? And in fact, I mean, you could have said interpolate, but you said extrapolate. And the reason for that is that the reason we do scaling analysis is because we want to make inferences about instances that are so large that it becomes very expensive to do experiments on them, right? That's much more useful than doing an experiment for a point in between here, right? And that's why extrapolation is exactly what you want to do. But first of all, if you don't do extrapolation, the classical thing you would do is RMSE, right? Root mean squared error, to just see how well you fit the data. That's the first thing. And so it turns out that with the RMSE, the exponential model is slightly better than the polynomial model, right? So you could, on that basis, and without having your clever thought, prefer the exponential model slightly. So now we're going to do what you said exactly. We want to challenge the model by extrapolation. And we do this by measuring two more data points, here and here. Okay. And notice this is the TSP. The running times get big pretty quickly. We fitted the model only up to here, to 1500. So 2500 is not just 1,000 larger. It's almost twice as large with something that has exponential scaling, or about exponential scaling. So it's a pretty significant extrapolation challenge. And so you can already see this falls short of the red line. It also falls above the green line, and now we can look at RMSE on those predictions, right? And that's arguably a better measure than RMSE on the data that we have just fitted. So let's do that. And to our surprise, the polynomial model now fares quite a bit better than the exponential model. Okay, so in that sense, the polynomial model is actually better than the exponential model for this algorithm. So this is interesting and unexpected. So maybe we need a third model that is a little bit more precise now, right? Because somehow this is in between exponential and polynomial. And what you might have guessed you could use is indeed this one here, square root exponential model. And if you fit this, you will see the blue curve almost perfectly hits those points. And actually the RMSE is an order of magnitude better than both of these other models, right? So I would claim this is already a more scientific way of talking about empirical scaling models.
Does the really small constant on your polynomial make you nervous at all? I mean, that probably isn't explaining what's going on.
Maybe it should, so we'll get back to that point. But this is a good observation, right? So the first thing that I want to point out, though, is even if we believe that the exponential is maybe a safe upper bound, look at the nature of this exponential, 15.04 times 1.0063 to the n. If we have to live with exponential, that's a pretty good exponential to have. I hope we can agree on that. And the polynomial is also not that bad. It's just a very small constant, as Cliff pointed out, times n to the 4, essentially. So it's pretty good scaling behavior, right?
This was uniform points in the plane?
Yes. And that's essentially what everybody who's doing TSP algorithms research with an empirical slant has been studying. And a lot of theoretical work, I think, has been focusing on that model as well. So it's a well-established benchmark, not believed to be atypically easy. And I'll give you some evidence for this not atypically easy in a moment. Okay? Good. So now if you want to further challenge the models, right, for instance, to see whether that small constant here should make us nervous, what you should do is measure larger data points. And there comes a big problem with that, in that actually behind every single one of these data points is a large set of instances, and there's quite a bit of variability in difficulty in these instances. We'll get back to that later as well. But for now, just take my word for it that some of these instances at 2,500 are actually an order of magnitude harder. And so as we go further up and challenge the models more, we will actually have runs that never terminate because we just can't afford to run them forever, right? And so therefore, we now switch from the mean to the median, because the median is not only statistically more stable, but also, of course, handles censored data very gracefully, because it can just cut it off until you reach 50% censored data. And so here is now observed median running times. We can now go to 4,500, so 3 times as large as the largest size that we've ever used for learning about the scaling behavior, right? So this is very massive extrapolation. And so we have an exponential model and its predictions here. Our best fit exponential model, we have our observations. This shows you how many instances actually completed, but because we're using medians, we don't have to be concerned. This is still statistically very safely away from the 50% point. This is our polynomial model, and this is the root exponential model. And you can see that the root exponential model is actually pretty close to the actual observations here, right? So almost on the dot for 2,000, almost on the dot for 3,000, and very close for 4,500 still, right? So this is actually very good for an empirical scaling model, and it might make you wonder whether there's a fundamental reason why it should scale that way. Now, I don't see him here, but I think one of you actually at least knows about a somewhat obscure theory result that uses a geometric subdivision technique to prove that in the worst case you can solve 2D Euclidean TSP in n to the square root of n. So that's a little bit worse than what we have here in our root exponential model. It's a log factor. But talking to the folks who did that, Nick Wormold and Warren Smith, they said to their best knowledge, nobody has ever implemented their technique. It doesn't make sense to implement it. And certainly Concorde, the solver that we're looking at here, the state-of-the-art solver, is not using any of this. And in fact, the makers of Concorde were blissfully unaware of this result at all. So this is interesting. And there might be some theoretical explanation for it. Kevin?
Two things. First of all, we can't see your red dot, actually, while I'm about to interrupt.
Oh, yeah, that's, I should just point like this.
But, and have you ever implemented, tried to fit the extra log factor?
Yes, and it doesn't fit very well. So it actually does open a gap that's, I didn't show it, but it isn't as good a fit as this. Okay, so the real question we should be asking, though, is how close is close enough, right? I mean, is this really a model we should have faith in as we go further out, or perhaps not? So it turns out that, RMSE and essentially just comparing those numbers, which is what RMSE is doing as well, is a little bit arbitrary. It allows us to distinguish between models, but it doesn't give us an absolute sense when we should trust something, right? And so what we want is a principled method for validating an empirical scaling model, okay? And so here is an observation based on which we can actually do this. So let's look behind the data that I've shown you so far. Let's run Concorde once on one instance, and this is what you get here, right? Another run, another run, another run, okay? So you can now see the variability that I talked about earlier, okay? Let's do this for 600, 700, 800, 900, and 1,000. And let's now boil this data down to medians, which is what we have done previously without me showing you. And then let's connect them through a line. And you can see that line is wiggly, and the reason for that is that here I only use something like 100 instances. If you use 1,000 instances, it becomes very nice and smooth indeed. And so then what we did is we fit it, and that's exactly what we did before. We do a best fit exponential, for example, to these medians, and then we measure, again, our target instances here. And we look at this median and we look at how close is this red dot to what the model predicts, right? That's what we've been doing so far. And now the key observation is, or the key question to ask is, what's the dependence of this empirical scaling model on the given set of sample instances, right? These instances that I actually had, how far do they influence the model? And that gives rise to the idea to actually validate the model using bootstrap confidence intervals by resampling those instances. You take the instances as a surrogate for the underlying distribution, sample from it. That's the classical bootstrap idea, right? And then you look at these samples and you see how that affects the model if you change the sample. And here's what happens. I take another sample. Actually, first of all, let's do a prediction, right? I take another sample, and you see that the prediction moves a little bit. I left a little trace of the old prediction so we can keep track of it. And it moves again, right? And if I do this 1,000 times, I get all of these points predicted, right? So I get a distribution of predictions. Now I can determine a confidence interval simply by determining quantiles, or there's more sophisticated methods, but basically just from this bootstrap distribution. So in this case, this is a 95% simple quantile bootstrap confidence interval between the center of this and this little red figure there. Good. And now I can see whether that median running time actually falls in between the two. And in this case, it just barely does not. It just barely falls outside of it. If that falls within that bootstrap confidence interval, in some very meaningful way, our model is in full agreement with what we've observed. Okay. So what we now get is bootstrap confidence intervals rather than individual model predictions. Okay. And we can now see whether they capture these observed median running times. And you can see those ones for the exponential model clearly don't. Those ones for the polynomial model clearly don't either, although it's not as far outside, right? And the ones for the root exponential model capture them just beautifully. You can also see how much uncertainty there is as you go further and further out in these model predictions, which previously we couldn't see, right? So in reality, the model is not saying that we get 400 or 334,000. The model says we get something between 253,000 and 734,000. And certainly 344 is nicely within that confidence interval. So now we know that in a very meaningful way, this and this model are not good models, and this one here, in fact, is. The next thing you can do is you can ask yourself, these little distributions, let's go back here, what do they look like? Maybe if I look at them, maybe if I can characterize them, we can find something useful. And here's something that I think you might be able to help with. I couldn't find it in the literature, but it might be a relatively easy theoretical argument to show that actually the distribution of running times of meaningful TSP algorithms should perhaps be a log normal, because that's exactly what we get. If we do a Shapiro-Wilk normality test here on those, this one here has a little bit of a tail abnormality because that's because the algorithm needs a certain amount of time to really get going. So there is some sort of startup effort that distorts the tail here. But these ones here get beautifully accepted by Shapiro-Wilk. So they are really basically perfect log normal distributions. And not only are they that, you can see in these cumulative distribution plots that also their coefficient of variation is the same. You can see that because these curves are basically exact shifted copies of each other, right? Now, once you know this, and again, it would be very nice to be able to prove it. This is just an empirical observation, statistically validated. Then you can basically have, and this is a log-log plot, which is why what used to be straight lines now is curved lines. Now you have basically a prediction for the median. You can derive from that predictions for also for your for the 005 and 905 quantiles, right? And so now you get a band in which all these instances should fall. 95% of them. And now you can do something very interesting. You can take structured instances, TSP-lib instances. These are not random. They are highly structured. Many of them actually come from problems such as drilling holes in printed circuit boards. So this is very, very different in structure from what you would expect in a random instance, because many of the distances are exactly the same because they're grid-based, right? Or we have in TSP-lib instances that are geographic, the 532 biggest cities in the United States and things like that. And you can see that these instances, the vast majority of them, falls within the band of predictions for random uniform Euclidean. And that is some sort of validation for the fact that random uniform Euclidean actually is a pretty good model for Euclidean instances, even structured ones. Okay, good. So what about inexact TSP solvers? This was an exact TSP solver that gets you provably optimal solutions. State of the art there, two algorithms, EAX, which is an evolutionary algorithm with a very clever recombination strategy. Very nice algorithm, no provable properties of any interest of this, highly heuristic, just like Concorde. And using our analysis method, we can show that its scaling can be characterized in the median as 0.25 times 1.123 to the square root of n. An LKH plus restart, and this restart is something that we added because we noticed stagnation in both algorithms. So they actually performed worse before we touched them, but they're very insignificant modifications. This one actually appears to be scaling polynomially. So here a polynomial model actually fits much better than the square root exponential, and a low degree polynomial as well. So this is trained again on 500 to 1500 city instances, and then selected based on the best RMSE on 2000 to 4500. But we already know that RMSE is not the best we can do. So let's look at bootstrap confidence intervals. And so I abuse notation slightly here by just writing directly the confidence intervals of the parameters, which you can of course extract exactly using the same technique, right? Because every curve that you fit to a resample gives you a model. And so you also get distributions over model parameters. And that's what I'm writing here. And as you can see here, actually, you get two models. This one here fits slightly better than this. But if you look at whether it passes the challenge in terms of capturing the predictions, it turns out this one here does capture, although it has a higher RMSE, it does capture. And this one here just barely captures not. So this, in some sense, is a lower bound, right? An empirical lower bound. And it's interesting that you can also see that LKH restart here tends to be a little bit better than EAX restart. And this is what you see in practice on those instances as well. All right. And so now you can have the idea, maybe Concorde, if I stop it once it sees the optimal solution quality without being able to prove that it is that, it's just as good, right? So you can, of course, analyze that as well. And you find, again, that this is a square root exponential model. But it is quite a bit larger in terms of the critical base of this square root exponential here than those two. So it is actually worse in a very measurable way, since worse. And in fact, I want you to notice that this confidence interval here is actually disjoint from this and this one here. This one here is barely disjoint from this one here. Yes?
Just to make sure I'm understanding, so in all these cases, you're aiming to find the exact optimum. It's like so stopping at 1% off from optimum might be much
exact
faster.
Optimum, absolutely. It is much faster. 1% from optimum is orders of magnitude faster. But we are ambitious here. We really want the absolute optimum. Okay. Of course, the analysis you can do for relaxed bounds as well. And who knows what you get. We haven't done that. So how about SAT solvers? You remember I told you earlier 1.32 to the n is the best worst case theoretical bound for 3 sets. So here we look at phase transition random 3 sets. So that's sort of the most famous case of randomly generated instances, has been studied by statistical physicists, theoretical computer scientists, and mathematicians for decades now. Some people used to believe, and I think still do believe, that phase transition random 3 set captures, in some sense, the essence of NP hardness, right? So what about this? We took 3 competition-winning solvers for these kinds of instances, KCNFS, March High, and March BR. So those were the 3 of a much larger number that we considered, and investigated the empirical scaling. And you can see that they're all exponential, but all exponential with very benign constants, very, very small prefactors, and very small bases here compared to the theoretical worst case. And that would explain why nobody is actually implementing this algorithm by Hadley et al. Because a difference between 1.32 and 1.03 is humongous, right? It's really big. Okay, so what about local search algorithm? Actually, first of all, we trained this here, and it did pass the challenge trained on 200 to 400. So actually, 3-SAT is quite a bit harder than TSP. You can really not solve instances with thousands of variables, random instances. You cannot. It's not possible. So we trained on 200 to 400, and then this passed the challenge at 450 to 550. At 550, you already have hours per run, essentially, right? If you were willing to invest months per run, you could maybe push it to 600, and then you would be absolutely topped out. And so you can see when you look at these bootstrap confidence intervals for the critical parameter here, they all overlap. And indeed, now you can do very fun things. You can say, if the real model were this, right, and I see whether it also describes the data generated by this guy, is it actually the case that we can say meaningfully this guy behaves differently from the model for this guy? And that is a more technical way of answering the question, is the performance difference between them significant? Right? It is actually a statistical significance test. And so when you do that, you find that these 3 are statistically indistinguishable, right? So you cannot make any claim that statistically any of these solvers is better than any of the others.
Are the algorithms similar in those 3 solvers? Are those 3 solvers using similar algorithms?
Yeah, to some extent, but there are significant differences between them. And actually, these ones won the competition years after this one had appeared. So empirically, this tends to be a little bit better, often enough that it can win a competition, but not often enough that you can say it with statistical confidence. So it might just be the competition samples due to which that happened. Or it might be a small enough difference that you would need millions of instances to tease out statistical significance. Okay? What about local search? Actually, some of the best theoretical results for 3-SAT are based on local search algorithms. In fact, this algorithm by Hadley et al. That I told you is a local search algorithm, right? So it only holds with high probability, which I neglected to say earlier, but I'm telling you now. So there's the famous Walksat SKC algorithm, which essentially rekindled interest in SAT in the AI community in the early 90s. Bart Selman will be here later this week, so he is actually one of the people who was majorly involved and for whom it's called S. The other are Henry Kautz and Brian Cohn. And you can see here, to everybody's great surprise, this actually scales essentially cubic, right, on phase transition random 3-SAT. And not only that, but the two sort of much more recent local search algorithms, PropZ and BalanceZ, also scale essentially cubically. And once again, we can do the bootstrap analysis to be statistically more significant or more sophisticated. And what you can see here is that these bootstrap confidence intervals for the exponent here are kind of wide, but they nicely bracket 3 in all cases. And again, there's no statistically significant performance differences between those three. Although in practice, when you look at it, this one would win a competition against this one here pretty much any time, right? But it's not enough. The margin is not enough using our modeling techniques to claim statistical significance. You would need many more instances for that. Yeah.
If you're only looking at like cubic with these small constants, why can't your challenges get a lot bigger?
That's a very good question. The main problem with that is that you would need a complete solver in order to make sure that you're not throwing out solvable instances that are too hard for these guys, right? Don't agree with the model, but that a complete solver can't solve. So it's the limitations in complete solvers that make it impossible to go further. These ones can go a lot further.
Well, you would know that 50% of the instances were solvable. If you were generating
Yes.
a lot of samples and solving half of them, you could maybe feel good about it.
And we have done this, of course. The big problem with that is the phase transition already at 1,000. And you notice we go to 1,000 here. We already go larger, right? The phase transition becomes so sharp that you can fall off in it in an instant, right? You can think you're at the phase transition and you see that you solve 50% of the instances or 50.3 or something, but in reality you miss the phase transition by 0.01 and 99% of the instances are solvable and you've just missed it. And that's the problem. That's why you can't confidently, without really going out on a limb, go beyond 1,000. But in principle, these solvers, of course, can tackle instances a lot bigger. You're quite right. Still not as big as the TSP instances that we talked about, but it's getting there. So there's a second thing I want to talk about now that I've shown you how to do analysis, scaling analysis in a somewhat more sophisticated way. And that second thing has to do with design. And Kevin will actually talk more in detail about that. I don't have the time today, but I thought I wanted to tell you a little bit how the two things connect. So if this is an algorithm, many algorithms actually have parameters, right, including all the ones that I mentioned today. And these parameters can be numerical parameters that you can just slide essentially, and they can be categorical parameters like pre-processing techniques you switch on and off, heuristics, A, B, C that you can switch between or freely combine, things like that. And we all know that by fiddling with this, we can make this guy behave better or worse, right, on given distributions of inputs. So we can go from low performance to high performance. And so Kevin, I, and quite a few other people have worked over the last decade or so on automating this process quite successfully. I want to show you a few quick examples, and Kevin will show you more and different ones. So this is Lingeling, a state-of-the-art SAT solver on software verification instances. The default configuration and a configured configuration takes only about a day or so to configure this thing. And what you see is that we get up to 2 orders of magnitude better on many of these instances, right? So this is pretty big. On average, we go from 3 PU seconds to 0.16. So these are all pretty easy instances, but you have to solve many of them in realistic context. It's software verification, so not just one. And actually, the rank of the solvers when you configure them may change very much. So in a competition where this thing in its default configuration competed with many others, it was actually ranked 4th. Once you configured all of them fairly with the same budget, this one ranked 1st. Right? So if you dismiss practically an algorithm just because it didn't win, it might just be that you couldn't configure it to win. Here is CPLEX, which we heard about earlier, which has lots of parameters on wildlife corridor design, conservational biology instances, default versus optimized. Again, you can see that's up to 3 orders of magnitude better. Average speed up of 52.3. And here's a fun little thing that I did together with Don Knuth when he finished his part of his Art of Computer Programming for SAT. Now you might wonder, if somebody like Don really thinks deeply about a SAT solver and builds one, then probably there isn't much potential for making it better by choosing parameters. And that's exactly what Don thought. And then Don and I intersected at some point at the SAT conference, and I gave a talk, not quite like this, but I talked about algorithm configuration, and he went like, well, maybe you should see whether you can squeeze something out of my algorithms. I don't think you'll be able to, but why don't you try, right? And so you will see if you read his book that he has an algorithm called SAT13 that kind of captures the state-of-the-art SAT solver architecture, very much like Lingeling. I actually trained this on instances just from down here. And Don made a nice set for it. And then when I evaluated it, it got quite a bit better here. It got even better up here. it's still, it wasn't as significant as in others, but this solver doesn't have many parameters, and it was Don Knuth who actually manually optimized the default down here, right? So it went, he's measuring running time in MEMS, it went from 0.57 to 0.40 gigamems, and a gigamem is something like 25 seconds on a contemporary machine. And that was a 41% speed up, and Don was very happy with that. He was very surprised. And so then we actually took these instances, and this is how it connects to scaling. We took this configuration and ran it on the instances that he was really interested in. These are called the TAOCP testing instances that the solver had never seen before, that were different in structure and that were much larger. Okay? And what you can see is that on these instances, it actually performed quite well. There's one outlier here, which both Don and I are not happy with, but not everything works well on everything, right? But on average, this actually came down quite a bit and essentially had a 36% speed up, which Don was really happy with. Okay, so the question now, however, is, can automated configuration improve the scaling behavior, right? Can I get to a better functional model, significantly better constants, for example? And that is the idea behind configuration for scaling. And so just very quickly, I want to show you some results that can be achieved without telling you too much how it's actually done, because that's pretty involved. But what you can do is this EAX algorithm, the default I showed you before scales like this. If you optimize it, it actually scales like this. And as you can see here, this constant here, which is of course the critical one, went down quite a bit. And these models here actually pass the challenges at most of these sizes here. So in some sense, this is statistically meaningful, the scaling behavior, right? You can go further using so-called parameter scaling models. What are they? Well, sometimes when you scale up an algorithm to larger instance sizes, some of its parameters need to be modified as well, need to be cranked up or cranked down, right? I'm sure you can all think of cases like this. And of course, if you know in advance, you can renormalize the parameters and then just fit constants, but often you don't know in advance. And parameter scaling models figure that out automatically using machine learning, essentially, right? And so we use these parameter scaling models automatically learned with configuration for scaling behavior. And what we get then is, this is what we had before. With these PSM optimization, we actually get down to polynomial behavior for EAX, which is pretty surprising. And the polynomial behavior, I should tell you, is slightly underestimating what's really happening, but better than any root exponential model that we can find that is automatically findable, right? So there's a little gap opening here, and we're still hoping to close that. So to wrap this up, my take-home message is this. In cases where you can't prove a nice theorem about the big O scaling behavior, or the constants, in cases where the constants hidden by big O are of interest to you, and often they are, there are ways of obtaining statistically sound models of empirical scaling behavior. Ones that have a statistical underpinning that is no guarantee it's statistical after all, but much better than just curve fitting or producing a little table. We can configure algorithms automatically for good performance scaling. So not just in the supervised machine learning sense where you have a representative sample from your underlying distribution, you optimize for that, which is already very cool, and you'll hear more about it tomorrow before lunch from Kevin. But you can actually do this so that you can have some statistical confidence that at higher instance sizes that you've never seen before, you will also be significantly better and the gap will grow, which is a nice thing to be able to do. And the methods that I've talked about here are very broadly applicable. There's nothing specific about them to SAT, to TSP, to MIP, to anything, right? You can use this for your algorithm. And certainly further improvements are possible. We are working on some. Hopefully, as other people pick this up, you will figure out more. The final remark I want to make is this. This area of empirical algorithmics, I like to use this symbol here for it. Not just because it's kind of an E and kind of an A, but because philosophically, it's an inductive mode of reasoning that's underlying the idea, right? And the inductive mode of reasoning is, I show you an algorithm, let's say Concorde, and I show you empirical evidence that this scales in a certain way. And then hopefully that inspires you to go and dig into Concorde, maybe simplify it, maybe dissect it, and ultimately prove theorems about some part of it. And that, in fact, is how theory is done in most sciences, right? You make observations, you generalize boldly from those, and then you prove something about them, right? So this is the inductive mode of reasoning, and it's very much what inspires empirical algorithmics. This, I think, is very nicely complementary and interacts very benignly and beneficially with algorithm engineering. And algorithm engineering, in my view, is something which starts from theorems and then tries to instantiate things that the theorems either leave open or that we feel we need to fiddle with in order to make the theorems applicable, or the algorithms about which we've proven something applicable to practical situations. We instantiate this and prove then there exists a variation of this thing that also works well in practice, right? From the general to the specific. So that's the deductive mode of reasoning. And I'm sure that many of you here prefer that mode of reasoning, but I think there is great complementarity between the two, and switching back and forth between those, like people like Donald Knuth and David Johnson have done throughout their careers, is indeed very beneficial. And I find working on this side here is a lot of fun and hopefully can inspire some of what's happening over here. So one last thing, if you find that empirical algorithmics might be cool and interesting, I'm working on a little textbook which will appear with Cambridge University Press pretty soon. So if you want to read more about these things, you can of course read my papers or wait a little for this. If anybody's seriously interested, I'm more than happy to share drafts. It's almost complete now. With this, I thank you very much for your attention and hope you found some of this somewhat interesting. Thank you.
So one thing that seemed really interesting, I didn't know, is that for exact solving of TSP, you said that so the random instances seem to capture kind of the same scaling behavior as so all these other things TSP-lib. Now, I mean, one could talk about that as for a particular algorithmic approach, or does it seem to be more than that? So, I mean, like that's, does it seem like that you've noticed that for a variety of algorithms? And would one, what
I have, and I find it very curious. I'm as astonished by it as you might be. I didn't expect that exactly. I didn't even expect it for Concorde. Our reviewers of the paper that we published on this 2 years ago didn't expect it either and were rather skeptical, but ultimately convinced. I think there must be something interesting going on here. And of course, adversarially, you can construct instances that deviate from this, right? You can look carefully at some of these instances that are outliers in this little plot that I've shown you, and then make more instances like that, and they will also be outliers. So this is not a result that says it always is the case, but it tends to be the case. So my feeling is that there might be a statistical result there that says, largely independently of how you attack TSP, as long as it's a general purpose TSP algorithm, the random uniform instances seem to be a pretty good surrogate for the kind of structure, for the kind of behavior that you will see. And it's interesting. I wonder how far it goes myself. Empirically, we've pushed it as far as we could, and we didn't find a real hole in it. No obvious hole. Now, special purpose techniques that are known to be efficient for very specially structured TSPs, I would not expect at all that this would hold for them. Obviously not, right? Because the structure that they latch onto would probably be absent in those randomly generated instances. Yeah?
So I have a question about your choice of models. I'm asking this because I'm thinking like machine learning, you're choosing models and then there's a number of parameters. So like when you say polynomial model, we call it A times, I guess, n to the b.
Yes.
So that's actually, I mean, that's more like a monomial model.
It is monomial, yes.
Okay, so if I, say, chose sum of 3 monomials, maybe
Yeah.
I would have gotten a better fit.
Quite possibly. I mean, almost certainly you would have. And the reason why we didn't is also the reason why you would expect that it would fit better, which is that, of course, from a rich class of models, a 6-parameter model or a 5-parameter model should fit better in principle than a 3-parameter or a 2-parameter model, right?
But if, say, my program does, say, 3 things one after the other.
Yes.
Maybe it runs certain heuristics in the beginning, and then I would try to add things up.
You are absolutely right, and the method that I try to share with you today is, of course, not restricted to 2-parameter models, not at all, right? In fact, you're perfectly fine if you have a hypothesis what the scaling behavior should be to plug in exactly the model that you want. In fact, we did a fair bit, I didn't talk about it today, we did a fair bit of fitting of 1-parameter models because we had reasons to believe that something should be fixed at some value, right? You can do that too. Ultimately, the limitation of the technique becomes the performance of the numerical optimization algorithms. It turns out to be the case that at 4 or 5 parameters, unless your data is very clean, the numerical fitting runs into bad local optima because most numerical fitting algorithms just guarantee a local optimum only, and even that, if it's a little ill-conditioned, can be problematic, right? So you need to have numerical sophistication to push through that barrier, but it's possible, right? And in general, the technique would just work. Another thing, of course, you can do is you can start with a monomial, you get a good fit for that, and then you start, essentially refining your model by adding more and sort of iteratively fitting those. And that's also something we've started doing, and that seems to be promising and working well. But you're absolutely right. That there are situations, and we can easily construct them, and we would also expect that they arise naturally, of course, where two-parameter models like the ones that I've shown you would not be the whole story, definitely.
So if the running times at a given instance size are log normal, couldn't you use that to do a better fit to your curves? Do a per instance size inference based on the log normality instead of taking the median, and a related sort of question is doing a different scheme, maybe trimmed mean or something instead of median. Why these particular choices to get a robust fit?
So median just seemed like the obvious choice. I would agree with you that trimmed means would also be possible. I think median is just more common, right? And median, I would claim that median performance means something pretty intuitive. It means the performance you see on 50% of the instances, including the 50th percentile, right? So I feel that that's a pretty nice thing to be able to say, that with a 0.5 probability, your running time will not be higher than this.
But you get better statistical efficiency, lower variance with other.
You're quite right. In my experience here, the major limiting factor is the sample size, not the inference that you're doing. And you're right that by using more powerful inference, you can deal with smaller samples a little bit better. And then it's the numerical fitting as well, which causes a lot of noise. So yes, there are definitely tweaks if statistical stability is your main objective, to improve that a little. I don't think you can improve it a lot on this data going to trimmed means, for example. Now, of course, your observation that if you have a distributional assumption, confirmed or not, at each instance size, you can exploit that is absolutely dead on. We didn't do it because we didn't want to contaminate our analysis with this assumption to start with. But of course, once you have it, you can then rework the analysis, and you would probably be able again to push a little bit further. Now, for as clean as distributions as we see here, the median actually is, the empirical median is a pretty good thing to plug in compared to something that's based on a fit of the entire distribution, as it turns out. So I don't think you would gain much. But again, I think you're right in suggesting there are data cases where you could gain much, and even here you might gain a little if you're willing to make this assumption up front.
So it's sort of a vague question, but given that you can do this configuration of algorithms, right? Should I be thinking about how to design algorithms differently? In other words, try to think about what's the exact right way to do this. Instead, should I be thinking what's like the right, space with knobs and then turn it over? I mean, is there any success in that area or any lessons?
Disclaimer, I didn't pay him to ask the question. Maybe, Kevin, you did? You're absolutely right. You couldn't, in fact, be more right. In light of what you just argued...
I paid you to say that.
We have been... Exactly. We've been advocating for a few years now something that we call programming by optimization. And the whole idea is that once you trust that you have a procedure that can do the configuration tasks better than you can manually, significantly better, right? Your approach to algorithm design changes fundamentally. It used to be, at least that's the way I've been brought up, and many of you academically probably as well, it used to be the case that you go, parameters are not so good, right? So let's try to make our algorithms parameterless, because users don't like to fiddle with parameters. And that's true. Most users don't like it and are not good at it either. We even found that most experts like us and Don Knuth are not that good at it, right? And that means a lot more. So the point is, once you believe that general purpose algorithm configuration is possible, it changes the way you think about algorithm design simply by encouraging you very much to leave the parameters in, to not make design choices by saying, I run a bunch of experiments and the constant should be 2.5 because that's what I've observed until I run out of patience. Instead, you say, I'm going to call this A, I make it a parameter, I leave it free, I might have some constraints on it, right? Because I know that it doesn't make sense to set A to 1,000,000, it doesn't make sense to set it to negative numbers, but then I let the configurator figure it out. And I think our group and other groups as well have started to really embrace this. You can see this as, in some sense, the generalization of the machine learning revolution, right? Why generalization? Because now we're talking about arbitrary algorithms, not just learning algorithms. We're talking about arbitrary algorithms, and you're encouraged to adapt them to the data automatically. In fact, using machine learning techniques and optimization techniques. And if you're interested in that topic, you will very much enjoy Kevin's talk, because he will do what I neglected to do out of time, namely tell you how this can be done. And it's actually a really interesting and cool way in how you can make this happen and get really good results.
So how close are you to making the entire code a parameter?
Sorry, say that again? How close are we to what?
To making the entire code a parameter.
Pretty far away, I'd say. That's kind of a dream. But there is an important boundary that so far we haven't overstepped, and I feel that it doesn't have to be overstepped to do really powerful and useful things. And that is the boundary where you are going from a space that only contains correct algorithms, perhaps even provably correct algorithms that differ in performance, can hugely differ in performance, to spaces that contain algorithms that might not be correct. So if you wanted to make your entire code a parameter, you would have to reason about spaces that contain incorrect programs. Okay. So then you have to not only do performance optimization, but also program synthesis. I think that's a phenomenally harder problem. Now, I do think, some of my work is on satisfiability, which can, of course, be used for software synthesis, right? My feeling is that sometime in the future, by bringing these two lines of work together, not necessarily me, but others, one could get there. But the way I think about it right now is that when you develop something that's performance critical, and it's not obvious what to do, and typically it isn't, right? Then you experiment no matter what. And what we're really saying is these experiments, first of all, don't do them in a haphazardous way, right? Don't do them in ad hoc ways, governed by your patience. And then never commit to anything hardwired in based on these limited experiments, right? Do the experiments automatically and be bold in throwing computation at them. And if you just do that, you will open up enough, right? So large parts of your code will still be written by you, and it will be you who's providing all the nice heuristic ideas and algorithmic ideas. And they might be taken from the theory literature for all that we know, right? Walks at SKC is very much inspired by the result, by the random walk result by Papadimitriou, right? So very good source of inspiration. You throw this all in, and then you let the machine figure out how to wire it all up, not to get correct behavior, you do that, but to get performant behavior. And that's the line that I would currently draw. And I think on our side of the line where we can work on this, we feel that we get a ton of traction. Past that line, super interesting work, but what we currently do only partially speaks to that work. Does that answer it?
Yes.
Good.
Thanks again.
Thank you very much.